All right, good morning. Please settle down. Right, so let's get started. Last week, before the break, we started looking at different models for electronic devices, right? For nonlinear devices, right? Mainly, we started with diodes and we looked at different levels of complexities. We looked at it as an ideal switch, on and off states, and then we said we can improve it by including a series voltage source, a battery, just to capture the 0.7 volts drop. But then we improved it further by adding a resistor in series with that too, to capture the voltage drop, right? So, those were the three models that we talked about. These were both, all three of them were piecewise linear models, each having a little bit more complexity than the previous model. But the actual model, the Ebersmall model that we discussed, was a nonlinear model that also we looked at. And then we started to go into the BJT. I posted the 3 lectures on 19th, 22nd and 23rd on the course web page. How many of you had the time to review them? Please raise your hand. Especially those who did not come for the lectures during that time. Didn't have time for anyone? Just one? All right. Well, the thing is this, you need to do that in order to cover the rest of it. So, I will try to cover as much as possible without relying on any of the previous notes, but please do watch the videos as quickly as possible, right, before we continue to further. Right. So, any questions from sections that we have covered so far? Any questions? Okay. So, no questions. Right. So, let's with a short review of the BJT modes of operations and the models, let's get started. We have covered the BJT, the first section in the previous class, but the video recording was not available. So, I won't go into too much details, the lecture note is there, but I will try to review what we did. Okay. So, we started with the BJT structure, the semiconductor structure, and we noted that there was, so if you get NPN transistor and you had emitter, base and the collector. So, we had this, we noted that they are not equally doped. We said the bias is slightly low, the emitter was highly doped. So, emitter had more dopant than collector, and base was only lightly doped, and also the emitter, the base was very thin, and that was important when we tried to explore how it behaved, right. So, this operation now, since there are two NP junctions, we modeled this as a back-to-back diode, while our actual IE actual behavior was VBE in this direction and the current, electrons go in that direction, the current go out. So, IE, we could model this using Ebersmall equation, IES, the reverse saturation current, e to the minus e to the BE, VBE, e to the VBE divided by thermal voltage VT, which is 26 millivolts minus 1, right. So, this is the nonlinear relationship between the current and voltage of this emitter current. We looked at it and we said when only one diode is connected, the current and the voltage can be well modeled using this Weber-Small model, right. Even when it is reverse biased, it behaved well. But the issue is when we connect this collector terminal also with a much larger positive bias towards the collector, much higher potential, the collector is at a much higher potential, then the what we described was the way currents and voltages appear in this particular circuit in this transistor cannot be explained using this particular back to back diode model, right. We noted that when you connect this using this particular setup, this biasing scheme, an electron entering into the emitter region of the PNP transistor could end up with 3 possible fates. One, it could exit from B. Two, can combine with a hole and lose energy as heat, right. B region, right. And number 3, because of this large pull, large positive voltage here, an electron here could jump over to the other side, to the depletion region of the base collector region, right. So, enter BC depletion region. So, we saw these 3 possible outcomes. So, go out here, combine here and lose energy, or jump over to the base collector depletion region. Once you are in the depletion region, because of this large pull, it could easily go into the collector side and complete the circuit, right. So, there will be a current in that direction, but according to this model you can't have a current flow if this is reverse biased. So, therefore, this behavior that we see here cannot be explained using this particular model, back to back diode model, right. And also we noted that by reducing the thickness of this base and also lightly doping it, we could reduce the probability of this and that and increase the probability of number 3, jumping over to the collector side. So, therefore, as transistor designers, they design transistors in such a way that they decide the doping level and the thickness of base and also emitter and collector to achieve a certain relationship. Typically, this allows us to get a relationship, a ratio between how many electrons jumps over to number 3 and how many exits from base. That is basically a relationship between the ratio between 3 and 1. Okay. So, I could design it in such a way like that. So, this ratio we called beta, right, which is basically the current exiting from the collector divided by current exiting from the base, right. So, this is, we cannot explain this using the Ebers-Moll model of the diodes. So, therefore, because of this external energy that we apply here, we introduce this external energy model. We call this an external energy model, external energy model. There are several external energy models, but this is one of them. In this case, that is described by IC divided by IB is a constant. Now, we have to remember this only works if you have a particular biasing scheme, right. This should be forward biased, this should be reverse biased, and that reverse bias should be much bigger than the forward bias there. Okay. So, we discussed about that. To capture that behavior, we so this simple 2 diode back to back diode model won't work. So, we introduced this to describe this, we introduced a current controlled current source. Output is a current which is controlled by the input current IB. Okay. So, we introduced a current controlled current source to this model, right. So, we have the base, collector, emitter. So, what we did was we had the back to back diode mode. So, this is the back to back diodes that you have, right. So, here one, and you could draw it here, but let me draw it here. So, these are the 2 diodes that we had, right. So, this is the back to back diode model that we start with, but to capture this new behavior we introduced a current source, a controlled current source. This we called IB dash, this is IB dash, this is IB, and this is IE, this is IC. So, this is basically this is how we modified it to capture this external energy model, right. And of course, diodes can be modeled using our previous discussion, either as a switch or as a switch in series with a battery, or a little bit further switch in series with a even battery and a resistor. But we are going to choose the middle one, battery with a ideal diode, right, battery in series of an ideal diode. So, therefore, this could be represented as, I have the base, right here the base connected to this diode which we mark as a ideal diode, which is basically a switch, on off switch, and back EMF or battery, right. This is a battery, right. And also this current controlled current source and another ideal diode in series with another battery. Okay. So, this is our new model where this is a on off, this is ideal diode, and this voltage when there is a current is 0.5 volts for silicon diodes. This is again ideal diode with this being 0.7 volts. Note the difference, this is 0.5, this is 0.7. Okay. Why? The 2 junctions are the substrates are not equally doped, they have different dopings. So, therefore, different forward drops. Okay. So, this is basically what we ended up with. So, we had the base, collector and the emitter. So, these are the three output terminals of a BJT transistor, NPN BJT transistor. This is what we looked at, and the voltage between this and that was VBE. This is VCE and VBC, right. VBC we do not typically care much about. So, that is where we stopped last time, said if I am right, right. Okay, so, we now have a model of the BJT. So, remember this is simply an on or off switch, right. Depending on whether these junctions are forward or reverse bias, you replace this and this with either a short circuit or open circuit. It is easy, right. So, once you have it, you can analyze circuits that contain transistors. So, note the difference in voltage drops. Across BC and BE. Junctions because of differences in doping, because of differences in doping. This will come, this will be important when you find the voltage across the collector emitter junctions when the transistor is saturated, right. You know, you might have done this during your first year. When there are 3 modes of operation, during saturation, the voltage across the collector to emitter remains constant at 0.2 volts. Where does that 0.2 comes? Where does it come? This minus that, okay. 0.7 minus 0.5 is 0.2, that is where it comes. Typically, if it is too small and you are working with large voltages like 10 volts or 15 volts, 0.2 you can even ignore and assume it is 0, okay. So, a model that even ignores this difference, okay. That is up to us to decide, right. Okay. So, this is where we were when we stopped it during the last class. So, any questions up to now? Right. So, with that let us move on. Let us, though you have done modes of operation for BJTs, let us review it again just so that we know everybody is in the same page, right. Modes of operation of BJTs. Now, since you have 2 junctions, depending on how many junctions are forward biased and reverse biased, there are 3 different modes of operation, right. Actually 4, but we can capture these 4 as 1, right, depending on the number of junctions forward biased, the BJT can be in 3 different modes of operation. Or states. For different states, right. The first is 0 junctions forward biased. So, that is both junctions are reverse biased, right. If both junctions are reverse biased, there will be no significant current in any of the branches, both the diodes will be off, so no currents flow through them. So, we call this the cutoff region, cutoff mode, cutoff mode. Second, only one junction, only one junction forward bias. Typically, that is the base emitter junction. There are two junctions, base emitter and base collector. The way the transistor is designed, we expect the base emitter junction to be forward biased, which means the base collector junction should be reverse biased. Okay? So, one junction forward, but what we are going to discuss is applicable even for base emitter junction reverse biased and base collector forward biased. One junction forward bias, the other one will also work, but with much less efficiency. Right. This is called active linear region, active linear mode, and this is the mode that we are interested about when we design amplifiers. We want the transistors to operate in this particular manner, like what we described here, right. This one reverse biased and this one forward biased. That is what we want in order to get amplification, because under such situations we have this behavior. Typically, this beta value is large in the range of 100. So, by controlling this IB, a small value, I can control a much larger current. I can generate a much larger current using this small current. Okay? That is where the amplification comes. Okay? That I can observe only if it is there. Okay? Number 3 is both junctions are, two junctions are forward biased. In such situations, this is open, this is short circuited, this is short circuited. So, what you have is a connection between here and here, 0.7 here, 0.5 here. So, what you have is voltage across this is 0.7. The voltage does not really change after that. The voltage will be fixed at 0.7. The current here will also be determined by the external circuit rather than this expression. This expression will no longer be valid when it is in saturation, when both the junctions are forward biased. So, therefore, it behaves differently, right. So, the behavior will be determined by the external circuit. So, it is a saturation. We call this saturation mode. This is the saturation mode. So, those are the three different modes. Let us now look at each of these modes and how we can model the BJT in each of these modes, right. So, the cutoff mode, so we want to look at models. So, what we have is the transistor is like this and it is biased in such a way that this is forward biased and this is reverse biased, right. So, this is the circuit. So, if you look at the back to back diode model, something like this, right. So, you have a reverse biased and forward biased diodes. This one VBE is forward biased and this is VCE and this is IB, this is IB and IE, IC. So, that is what we have. The voltage is VB, right. So, this voltage is VBC. So, example voltages, let us say here is 0 volts, this may be 10 volts and this may be 1 volt. Yeah, You have to speak loud.
That diode is forward bias.
This diode is forward bias. This diode is reverse bias. This you have positive here. That means it's reverse bias. Okay. Any mistake here? Yeah. Still. Oh, yes. Thank you. So this is the cutoff mode I am drawing now, not the active linear one. Thank you very much. You get 1 point for this mistake, right? So you have to give me the registration number after. Thank you. All right. So this is, thank you very much, a genuine mistake, but I'm glad that you were able to capture it. So this is, what we want is both reverse bias. So I was looking at a different picture, right? So let's redraw those. Okay. So what we have is, this is reverse biased and the other one is also reverse biased, like that, right? Correct. That is for the cutoff mode, sorry. You see, so like that, right? So VBE is less than V forward of the base emitter junction. This voltage is less than 0.7 positive, right? So now it's negative. And VBC is also less than V forward of base collector junction. They are different, right? 0.7 and 0.5. Remember, we had different values here. This value is about 0.7 for silicon diodes. This is about 0.5 for so therefore, both are reverse biased, no significant current, flow in any branch. So these currents IB, IC and IE all are 0. All are 0, right? VCE, since there are no currents, this whole voltage, whatever the voltage, that will be there, but we don't care. We don't care. If there is a voltage difference here, that voltage will appear there, but we don't really care. The power is IC times VCE. VC will be some finite value, but IC is 0. So therefore, power dissipation across this transistor is 0. No significant power is lost. Okay, no heat generation. Right, that's still cutoff mode. So let's draw this in the model, using the model. So what is how can we model it? So I can model using my previous model. So I have an open circuit diode and this 0.7 volts here, and I have an open circuit diode and the voltage here, and this is this doesn't apply into this mode, right? Remember, it's not applicable to this. So therefore, my model becomes like this: base, collector, emitter. So, as you can see, there is an open circuit here, there is an open circuit here, there is an open circuit here. So, what you have is something like base, emitter, collector, something of this nature. That is the model that we have. So, VBC, base to collector voltage, is less than 0.5, why 0.5, this is 0.5. If it was conducting, but now we are modeling it as a battery, no. So, whether it is conducting or not, it is there, but this is open circuit. So, therefore, will not work. And this one 0.7 VBE, because this is open circuit, VBE will be less than 0.7, right, and all the currents IB 0, IC 0, no current pass, and IE all the currents are 0, and the voltage between the emitter and the collector VCE can be anything. You can have any voltage that is applied externally. Okay, so this is an open. These are 0. So, there is nothing much to worry about, everything is 0, nothing to actually analyze, everything will be 0, the voltage will be determined by the external circuit, that is it, right. So, that is not very interesting. So, let us now look at the more interesting one, the active linear region, the second mode. Active linear mode, we know one forward bias junction, typically BC, BE, sorry, and one reverse bias junction, typically BC. Since B and C are not equally biased, they do not behave identically. So, you can't interchange the base and the collector in general. You can't expect the transistor to behave the same way if you interchange base and collector. However, even if you change these terminals, it will kind of work, but instead of beta being 100, beta will be something like 5, very small gain, right. So, it is not what we want, we want it to. So, typically we do not use this reverse, we call this this other one reverse active region, we typically do not use it, right. So, but by the looking at the model, you can't differentiate that, right, you can't differentiate that using looking at the model, right. So, what we will have is something like what we drew earlier by mistake. Something like that, that is for the active linear region, right. So, this is basically what you have, and if you look at the back to back diode model, like this, and the currents and voltages IB, IE, IC, VBE, VCE, VDE. So, will be like that. Now, this diode is forward biased and it can be properly modeled using Ebers-Moll model, right, only one, because we do not have so the first one can be this model, this diode only can be modeled forward biased base emitter junction can be modeled as a forward biased diode using so this is Ebers-Moll EM model. You can model it using that. That means IE is equal to this current can be written as reverse saturation current V B E sorry e to the V B base emitter divided by V thermal minus 1, which is roughly equal to IC. So, this holds for that. Now, note that collector to emitter voltage is high, right, because you can see this whole voltage is across collector to emitter, this plus that, and there is a large current IC which is modeled here, right. This current is also high. Because of that, there will be a large power IC VCE, large power dissipation is there, though it is going to heat up, okay, VCE IC across the terminals, large power. Okay, it is going to dissipate. Now, what if how about the second junction? Now, the first junction base emitter junction we could model using Ebers-Moll, but for the second one, for this one we said it does not behave like a diode, it has this current controlled current source behavior, right. So, therefore, from external energy model, beta equals IC over IB is roughly about 100, can be actually this value 100 varies with temperature, it is highly sensitive to temperature, but in our model we do not capture it. I said in abstraction sometimes we omit certain behaviors, right. So, in this abstraction or in this model we do not take into consideration the behavior of beta with temperature, but actually you cannot ignore it. This sensitivity is not 10% or 5%, it is much bigger. If you change the temperature, this beta value may vary from 100 to 50 to 250. So, it is not small variations, right. So, therefore, we provide these values, typical values, lowest value, highest value, the range we give in these data sheets. So, if the temperature varies, the beta value we have to take into account that variation. Okay. So, under such situations VBE is greater than forward bias voltage of base emitter. So, it is roughly about 0.7 volts. VBC is less than V forward bias of base collector junction. So, which is 0.5, less than 0.5. So, we draw the model of this in the following manner. So, you have the short circuited or open circuited short circuited diode. Here also you have the short circuited diode with so this is also short circuited, this is also short circuited. and this is 0.5. This is the current source, and this is 0.7 base collector emitter. So, this is VBE, it's a positive value. This is VBC, it's negative because it's reverse biased. This is VCE. This is VCE. IB, IC, IE. The currents flow like that, and this current IB dash and this current is beta times IB dash. Okay, so that's my new model. Sometimes we simplify this because voltage across current source varies and it maintains its current. So, therefore, sometimes we simplify this to bring this voltage source up to here, right. So, we sometimes draw it like this. Simply like this, base collector emitter. .7 volts, beta times IB, and IC, IE, IB. Okay, so we see. For this to happen, E should be the smallest, VB should be greater than that, and VC should be even greater than that. Yes. So, reverse active mode will be similar except that beta will be much smaller, right. Reverse active mode this will work, but not efficient, meaning that beta will be much smaller. Any questions? I can hear Kasukusu. Any questions? Please ask me. Right. BJT is designed to work with base emitter junction forward bias and base collector reverse bias. So, therefore, we typically do not use this mode. Right. So, the third, so we do not typically use it. So, let us look at the saturation mode, the third mode. saturation mode, in which both the junctions are forward biased. Base emitter and base collector junctions are forward biased. So, VBE is greater than the forward drop of VBE, which is 0.7. VBC is greater than the forward drop of VBC, which is roughly about 0.5 volts. So, with these two there, VCE, which is actually equal to VBC VBE minus VBC, which is like 0.7 minus 0.5 is 0.2 volts, right. This is your and this relationship beta equals IC over IB does not hold. It's not. Beta is, the ratio IB is much bigger now. So, therefore, IC is less than beta times IB. IC is less than beta IB in saturation. Okay. So, the current IC, which is also equal to IE roughly, maybe actually this may not hold all the time under saturation, because there can be currents that are comparable to IC in the base, right. So, I would not like this, write this IC and IE. IC, IE are determined by the external circuit. External circuit. And the power IC, VCE. Now, IC is large, but VCE is roughly 0.2 volts, which is roughly equal to 0 compared to the voltages that we work with. So, therefore, very small power dissipation, almost 0 power dissipation, not much power dissipated in this scenario. Okay. So, we can model these models. We can use the same model now. The only thing is this won't be there, this won't work as it is. So, therefore, my model simplifies to the emitter, base, and collector. This is 0.5 volts, this is 0.7 volts. So, therefore, VCE 0.2, roughly 0.2 volts, IC, IE, IB. So, combining this, we sometimes, if this value 0.2 is too small to, if we are working with larger voltages, we can even simplify and ignore that and get something like this, the simplified version. Okay, base, collector, emitter, this is 0.7. So, in that case, we simply ignore the 0.2 volts there. Okay. That is a simplified model. So, here base is at the highest voltage. Now, these are some models, but there are other models as well. There are more complicated models that can capture more details in more accurate form, but at what cost? With more analytical complexity, right. For most of our work, these models are good enough. Okay. So, we are going to be satisfied with this accuracy. Some other more complex models are also available. For example, there is a BJT Ebers-Moll model. Okay, so where we talk about I alpha, I beta, all sorts of things, forward current and things like that. We are not going to discuss it in this particular course. Okay. Right. Any questions up to models of BJT? Okay. Let's move on then. So, let us revisit what some you have already done, the output characteristic of the BJT. Right. What is output characteristics? The relationship between output current versus output voltage. What is the output current? IC. What is the output voltage? VCE. So, it is basically nothing but a relationship between VCE and IC. Right. You have already seen this. We have already seen this. You know that with different input currents, output current varies, right. Obviously, IC depends on IB also, right. IB depends on the, so therefore, in this case, we can't just have one line depending on IB, for different IBs, I should have different curves, right. So, I am pretty sure you have already seen this. Something like that. You have seen this, right? You have seen this. So, here the voltage where, so these separate lines, I can call this IB equal to 0, base current 0, IB is IB1, IB2, IB3, IB4, IB5. So, different levels. Obviously, there are infinite number of such curves in between for different IB values, right. This where this IB is equal to 0, this region, we call this, what do you call this? What mode? When the transistor has IB equal to 0, We call this the cutoff region, right? It's cutoff region. It's called the cutoff region. And where you have very large currents without much VCE. Very small VCE, but large currents. That's basically this region here. That region is called the saturation region, so saturation mode, fully on or saturation region. Or we can call this the on state, saturation region, and this the off state, on and off. If we are going to use the transistor as a switch, on-off switch, to control the current, this is the mode you will be working on, right? In such situations, either voltage is very small or current is very small. In between this area, we call this the active linear region. This is called the active linear region, where we have this IC. If you say, look at this, these lines are parallel. So, therefore, there is a relationship IC over IB is a constant beta, right. This characteristic holds there. Now, though we do not typically look at it, any transistor, when you package it and when you have large currents and voltages applied, there will be VC times IC power dissipated as heat. So, when you heat things up, what will happen? That beta, I say beta will increase. What is beta? IB, which is basically a constant, divided by IC divided by this. So, if beta increases, that means instead of IB is constant, IC will not be here, it will be more than that, right. When that happens, even more current flows. That means more power is generated, more heat is released. When you release more heat, temperature will go further up. Now, depending on how you package it and where the medium is, there is a certain limit at what rate heat can be taken away in this environment. If you put it in air or insulated media, you can't take much heat out. But if you have a good water or some liquid cooled system, you can take out a lot of heat out, right. So, depending on the situation, if the transistor is producing too much heat, then the environment can take it out. There will be heat accumulation, meaning temperature will constantly go up and up and up. As temperature goes up, beta will increase further and further, increasing IC even further, and what will happen? There will be too much heat and it will burn the transistor. Okay, so that is called the breakdown region, right. So, there is a breakdown region where VC times IC is a constant, which is the power, and that is the power at which the external environment can dissipate heat. If it above that, it will start with. So, therefore, there will be a region like VC times IC. If you draw a constant line, that is basically a hyperbola like that. So, anything above this will be, that is called the breakdown range. There P, VCE, IC is much bigger, very high, right. So, that is basically called the output characteristics. You have probably done this experiment and you have obtained this output characteristics in your first year, is that right? there was a practical on this, right. So, you know what this is. That is the output current versus output voltage graph. Now, there is another similar graph which we use often in characterizing circuits, which is called transfer characteristics. This is output characteristics. The other one is transfer characteristics. Transfer means how input is turned into output. So, that is a output versus input characteristics, right. So, it is called transfer characteristics or input output characteristics. So, if you have a transistor circuit like this, and if I connect this into some voltage source, this voltage VBE, that is the voltage that I directly connect across the base emitter junction, right. And by doing that, I basically control this voltage. What I want is to find the output. VCE. Okay. So, VCE is the output, the current IC. So, if you look at just the transistor alone, what you have base, collector, emitter, right, where this is the input VBE and this is the output VCE. So, I am going to plot, I want to see the relationship between VCE and VBE, right. Now, the issue is there are 3 regions of operation for the BJT depending on the value of VBE. If VBE is less than 0.7, that means my transistor is in cutoff region. If it is in cutoff region, there is no IC, IC will be 0. If IC is 0, there will be no voltage drop across this resistor. If there is no drop across this resistor, since this voltage is VCC, this same voltage will appear across the output. So, therefore, if my VBE input voltage is very low, less than 0.7, output will be equal to that supply voltage VCC. So, we can apply, so in order to get it, we can first apply Kirchhoff's voltage law to the CE loop, output loop, right. So, VCE, V out is VCE plus ICRC, so this plus this should be equal to VCC from Kirchhoff's voltage law, right. So, that is simple enough. So, this gives me VCE is equal to VCC minus ICRC. Now, what I am interested about is not a relationship between IC and VCE, that is actually the output characteristics of the transistor. What I am interested about is VCE and VBE, input voltage. So, then I need to replace this IC with some function of VBE, right. So, that is my goal. So, I look at the 3 regions separately when cut off when the system is cut off, VBE is less than 0.7, IB is equal to 0, IC is equal to 0. If IC is equal to 0, in this equation, if IC is equal to 0, VC is equal to VC, right. If I call this equation number 1, right. Because of this, from 1, VCE is equal to VCC. That is a relationship, right. So, if I want to plot VBE VCE relationship, if it is less than 0.7 volts, right, that is when it is cut off, I have VCC value. It's like that. So, I know transfer characteristics up to 0 to 0.7 VBE. Right. Next is when saturated. When saturated, we know that VCE is equal to 0.2 or roughly 0 volts, right. Let us say 0.2 volts, 0.2 volts, right. Yes. Which one? When saturated?
Yeah, it should be VCC constant under 0.5, right?
Point, this one, right? Ah, yes, this one. Ideally, yes. Ideally, this should be something less than that. 0.7 is, so let's put it as 0.5. Anything that you have, very small currents, right? Thank you. You also give me your number, I will give you credit for that. See, I am generous, okay. So, I want you guys to contribute, I am giving back, okay. Right, got it, look, okay, agree. This is 0.5 volts, I have up to this, yes, you are correct, my mistake. Right, so now that is also fine. So, therefore, second case is also fine, VBE is less than 0.7, typically up to about 0.5 there will be very small current, and sorry, in this case VBE is 0.7, no more, greater than 0.7. Okay, so 0.7 volts and more, I have saturation. I have saturation, this is about 0.2 volts, correct. So, that is what you have. Now, you have two regions covered, right. Under this situation, IC is equal to VCC minus 0.2 divided by RC, the current, if you want to find the current, very simple, right. The third region is active region, when active linear, inactive region, inactive linear region, active linear region. We know that in this situation, IC which is roughly equal to IE, which can be written as the Weber-Small equation, right. Active linear, remember in active linear region IB is very small, IC is, because IC is equal to beta times IB, beta is like 100, IE is equal to IB plus IC. So, like 1 and 100 times 1 beta, sorry, IB plus 100 IB. So, 101 IB, right. So, therefore, we can say 1 you can ignore. So, therefore, IB is, if you ignore the small part, IC is roughly equal to IE. IE and IC are equal, and we know IE obeys the Ebers-Moll criteria, forward bias current, right. So, therefore, this is equal to reverse saturation current IS e to the VBE over VT minus 1. If you want, you can have it, but remember this is a picoamperes. Now, IB in saturation is much bigger in milliamperes. So, therefore, I can easily ignore that minus 1 part. So, this is roughly, you can keep that minus 1, it will make the model even more complicated, but this is good enough. So, therefore, I will put it almost equal to, right. So, therefore, now I have in place of IC a VB. So, therefore, in that equation number 1, I can replace this IC with this nonlinear component. This is nonlinear. Now, up to this everything was linear, nice. But now, when I replace this, VCE is equal to VCC minus IC, which is basically IES, which is picoamperes, some small value, e to the VBE divided by VT. That is what you have now. If you want, you can have minus 1 also. So, what this describes the way, so when VBE is equal to 0, this is equal to IES, which is almost 0. So, you can ignore this, this will be equal to VCC, right. So, it starts with, so VB is equal to 0.5, right, 0.5 or very small. When it is very small, like close to here, it will start from here when VB is small. When as VBE increases, this grows exponentially, and this is subtracted by this. So, therefore, it is an exponential increase, but subtracted by this. So, therefore, it goes like that, but then it gets saturated towards the end, right. So, this is basically how this looks like. This is the edge of saturation. So, we call this B and A. B is edge of saturation. The behavior from here to here, this is called the cutoff, input output relationship. From here to here is active linear region, and from, let us use another color, here saturation. Okay, so, this is called the voltage transfer characteristics. Okay, so, this is the voltage transfer characteristics. Any questions? Because we are going to move on to MOSFET. Questions? Nope. All right. So, these are some of the tools that we are going to use in the future in analysis. Ready to go to MOSFETs? Okay. Models for MOSFETs. MOSFET models. Right. So, if you can remember, let's work with N-type MOSFETs. MOSFET like this. This is the gate, drain, and source, right? Because of the oxide layer, typically for MOSFETs, input current is 0, right? There is not much current, so Ig is equal to 0. The current that goes through this, so therefore, goes from D to S, so therefore, we call this IDS. IDS, and this voltage between the gate and the source we call VGS. This voltage between drain and source we call VDS. And gate is nothing but a control port, control terminal. And the current enters here, we call this the input terminal. And this is the output terminal. Right. So, this is we know when you apply a very small voltage between the gate and the source, like 0 volts or anything below a certain threshold, we call this the threshold voltage Vt. Between 0 and Vt, the gate to source voltages, there will be no current through the transistor. VDS will be 0, IDS will be 0. So, that is like a switched off or open circuited switch. But if you increase it above V threshold, then there will be a current flowing through the drain to source. So, in the simplest most possible mode, I can ignore the resistance inside or anything else and look at this as a open switch and a closed switch. When VGS is less than a threshold voltage, it is a open switch. When gate to source voltage is above this threshold voltage, switched on, there will be a current. Current will be determined by the external circuit. So, it is a switch, right. So, that is the simplest possible one. So, we basically have a control terminal and a switch. So, it is a 3-terminal switch, right, 3-terminal switch model. We call this S model, switch model, right, switch model. Okay. When VGS is less than, let us call this is large, high, as in the digital circuits, right. So, most of the digital circuits basically use MOSFETs. So, in digital gates, high means a voltage applied and low, right. So, high and low. So, when this is the case, VDS is very small. Now, what is the circuit here? We forgot to draw the circuit. This is the output VDS. VGS, gate, drain, source, right. So, when there is a large current, there is no voltage drop across this in this simplest model. So, therefore, all the voltage will drop across RD, output will be 0 when this is on, that is when VGS is greater than a certain value, when VGS is large, high. If VGS is very small or less than a certain threshold, there will be no current through this. So, therefore, there will be no current voltage drop across RD. So, therefore, this VDD is equal to the VDS. So, therefore, VDS will be high, right. So, VDS is roughly equal to 0, very small. So, act like a closed switch. It's like a closed switch. Similarly, when VGS is low or very small, then ID is equal to 0. If ID is equal to 0, that means, remember how do we characterize an open circuit? ID is equal to 0, right. We do not care about the voltage, right. So, this means acts like an open circuit, open switch, right. So, we can model it like that. So, the switch is closed when this is high, gate, drain, source, high. When this is high, I have a closed switch, this ID is there, VDS equal to 0. VGS greater than a threshold, some value, right. So, when it is low, then when it is less than VTH, current ID is equal to 0 and there can be VDS, depending on the external circuit, this value will change, right. So, this is like on off switch like that, okay. So, if you draw the characteristics, IV characteristics, VI characteristics, then it will have piecewise linear characteristics like this. Here VGS is greater than some threshold, here VGS less than V threshold. That is your VI characteristics. Remember, we are going to characterize our elements using VI characteristics. So, you do not have to worry about anything else, as long as you know this, it is just another element, right. Similarly, the output the transfer characteristics. Transfer characteristics, that is input output characteristics. What is the input here? Input is this. So, therefore, my input is VGS, output is VDS, right. So what will happen to, so this is the circuit. V out, V in. If this is my threshold voltage, if VGS is less than this, VDS is equal to VDD. If it is greater than that, it will be equal to that. So, that is my input output characteristics for the S mode. Okay, so, S model. Right. So, input output characteristics and VI characteristics, those are the two graphs I have given here. Right. Let me see. I think it's almost, it's 12:30 now, so I think it's better to stop our today's lecture. On Friday, we'll start from here and discuss about few more models for the MOSFET, and then we will move on. Yeah, I think we'll talk about several models in the next class. All right, any questions? Questions? All right, if you don't have any questions, you may leave. Thank you, and you too will have to give me your numbers.